Hello, everyone. This is Mohammad Khoshan, the Technical Chair of Texas Power and Energy Conference, TPEC 2021. Today, we are having our second plenary session on the reliability challenges in high-density power electronics design. It's a hot topic in the field of power electronics with lots of ongoing research and studies, and will become even more interesting with the eminent panelists and the session chair who are from both academia and industry sides. I will quickly introduce the esteemed session chair and panelists. The session chair is Dr. Alex Hanson. He is an assistant professor at the University of Texas at Austin. He received his master and PhD degrees both from MIT in 2016 and 2019. His research interests majorly include component and research system level power electronics, high frequency magnetism and circuits, and leveraging power and energy in medicine and aerospace applications. He recently made their novel work on wide operating range, resonant transition sub-switch converter, a US patent. The first panelist is Professor Alan Mantooth. He carries 10 years of industrial experience at Texas Instruments and Analogy Incorporated before joining the University of Arkansas in 1998, where he is a distinguished professor now. He has co-founded two companies, Linguent and Ozark Integrated Circuits. He is the immediate past president of the IEEE Power Electronics Society. He has conducted many projects on analog and mixed signal IC design and computer-aided design, power electronics, and semiconductor device modeling. The next panelist is Professor Thomas Jahns, who is a Grainger professor at the University of Wisconsin-Madison from 1998. He received his PhD, actually all of his degrees from MIT. He worked at GE for 15 years, where he made an impressive contribution in developing IPM synchronous machines that are used in nearly all commercial hybrid and battery electric vehicles produced today. Dr. Jahns holds 16 US patents. He also received the 2005 IEEE Nikola Tesla Award. His research interest includes power electronics, electric machines and actuators, adjustable speed drives, and automotive and aerospace electric systems. The next panelist is Dr. Hans Stork. He's the Senior VP and CTO at onsemi. He received his PhD from Stanford University and carries around 30 years of industrial experience. Prior to onsemi, he served as the VP and CTO of the Silicon System Group at Applied Materials and Senior VP and CTO at Texas Instruments. During his career, Dr. Stork has worked with some of the semiconductor industry's leading innovators, including Hewlett-Packard and IBM Research. His chief skills include R&D, semiconductors, technology development, and cross-functional team leadership. Finally, we have Dr. Sreekant Narumanchi, a PhD graduate of Carnegie Mellon University, who is the manager of the Advanced Power Electronics and Electric Machines Group at NREL. His team is conducting really interesting projects at NREL with the focus on the systems for electric drive vehicles that control the flow of electricity among the battery, motor, and other powertrain components. His broad research interest includes heat transfer, power electronics, and motor thermal management, packaging, and reliability. With this brief introduction, I invite Dr. Hanson to commence the session. Thank you.
All right, thanks, Mohammed. I don't really have all that much to say. I'm the moderator for this session, so what I'm going to do is I'm just going to monitor the question and answer section during the presentations of the various speakers. So for those who are attending, if you'd like to ask a question, please go ahead and put it in the question and answer section just as soon as you have it, and I will monitor it, and if it's immediately pertinent, I might bring it up, but I'll probably save most of them to the end of each presentation. We'll have each of the speakers speak for 10 or 15 minutes or so, with a few minutes of questions for each. And then hopefully at the end, we're left with 15 or 20 minutes to have a little bit of open discussion, and that'll take us through the whole thing. So with that, I'll stop talking and pass the time over to Professor Mantooth. And like I said, if you have questions, just go ahead and put them in the Q&A section, and I'll be monitoring that.
Excellent. All right, so hopefully you can hear me and see my slides, and we're good to go. All right, thank you. I got the thumbs up. So, well, good afternoon, everyone, or wherever you might happen to be in the world watching this these days. We have to be a little careful where we do our greetings, I guess. But it's my pleasure to be invited to talk to the conference today on reliability challenges in high-density power electronics. And, well, this is something that you sort of asked the question. Power density, efficiency, these are all things that are very important, but at what cost? And at the end of the day, reliability is one of those things that is going to be the cost if you don't pay attention to how the system is designed from the beginning. And that'll probably be my conclusion right there, is that, you know, we have to be willing to factor in reliability as one of the axes that we're considering when we're looking at multi-objective optimization of the high density power electronics that we design today. We hear about efficiency and volumetric density and in some cases gravimetric density and other things that we want to consider cost, of course, all of these being axes that we care about, but reliability certainly has to be a part of that. And so by way of introduction, of course, I'm a professor at the University of Arkansas, as I was introduced, and I lead 3 centers of excellence there. One is the Cybersecurity Center, which has nothing to do with today, but it's on energy delivery systems. And then GRAPES, our Grid Connected Power Electronics Systems Center. And then POETS, I'm a deputy director of the ERC on essentially electrothermal systems, which is focused on transportation. So I draw some of the things that I'll talk about today from those experiences. So in this particular slide, you should see a number of prototypes that these centers and my colleagues and myself have produced over the last 3 or 4 or 5 years in terms of transportation and grid-connected power electronics, and they range from the kilowatt scale up to the megawatt scale. And the point being that we're using these wide bandgap technologies, whether they be gallium nitride or silicon carbide, to sort of drive the volumetric density and the efficiencies. But of course, one of the things that we've also taken a great deal of care in the last, I would say, 3 years is what is going to be the reliability and how do we model that? And so I think, you know, there was no particular point for me to make on this slide other than to say that as you start looking at these various prototypes, some of them are quite power dense and on the order of, say, 100 kilowatts per liter, and others, you know, starting out, say, maybe 2014 timeframe, we would see 10 kilowatts per liter as sort of the standard. So in 5 or 6 years now, 6 years, we would see this moving up to, you know, a factor of 10x. And so what happens when we have to consider the reliability? So, well, one of the things that you're obviously always concerned about is the components that make up your system. How reliable are they? Can the system even be any more reliable than its weakest component? And of course, the answer is no. But where I'm coming from with power electronics in this case is so much of power electronic systems are built upon power modules. Not all of them, but many. And so I'll just focus on that just a little bit. One of the things that we learned from VLSI is that integration is a great way to improve reliability. So just because I have more transistors on a chip does not necessarily mean my chip is going to be less reliable. And in fact, I believe it was the Intel CTO who said about 20 years ago, you know, transistors are essentially free on a chip. And so if you need to add another 10,000 transistors, 100,000 transistors in order to make the design more reliable, to make it more testable, add them, because we're putting billions of transistors on a chip anyway. And so in that vein of thinking, what might we be looking at when we're talking about power electronics? Of course, transistors aren't free when it comes to wideband gap power devices, that's for sure. But as we begin to see the different circuit architectures that our clever circuit designers from around the world are coming up with, one of the things we're seeing is that increasing complexity is not necessarily sacrificing reliability. And so and integration is actually a key aspect to that, the point from VLSI. And so one of the trends that we're seeing as it relates to reliability for high power density is how do we integrate more? Integrate more inside a package, integrate more on a particular circuit board. And so when you're looking at this particular module in the upper left, that's a sketch of a module we'll be building that's 1.7 kilovolts and 1.6 kiloamps. Okay, it's going to be thermally limited. And so it is an electrothermal design. And we're going to be focused on how do we manage, all of the reliability considerations, not just the electrical and thermal, but a first order effect on reliability, because we don't want to see warpage. We don't want to see other things that would sacrifice the lifetime of this module. Because this is, again, a building block that goes inside something like one of these megawatt class grid connected converters, for instance. So when you look at the 3D double-sided cool module, again, focusing on even greater power density, where we're cooling both sides of a module like this, and we're building in things like gate drivers. So this little PCB you see here is actually something that would be inside this module and would be routing all the gate signals, taking some sensed signals from within the module, such as thermal type of sensors, or perhaps Hall effect devices that are integrated inside the module. We're able to instrument the module, monitor it, and monitor the reliability or monitor the lifetime of the device real time. So in one way, this helps us prevent catastrophic failures in the field, because we can see when something is going out of spec, and we can begin to apply the data algorithms that we're going to be known for in this field before very long to do prognostics and diagnostics. And so again, this is the sort of thing where I think integration within the module, within the package, is actually going to assist us. Yes, we're adding additional components, but if those are highly reliable components to begin with, we're improving the reliability as opposed to sacrificing it. And then this last photo in the lower left corner is a reticle of silicon carbide integrated circuit, which holds about 40 different integrated circuits that can operate up to 400 degrees C. Now, even if we're talking about domestic, electronics that we're not trying to fly to Venus or whatever, and we don't need to worry about 400 degrees C, the fact that they can perform at that temperature means they can live inside this module and reach junction temperatures of 175 or 200, and it's not going to sacrifice their lifetime or reliability. And so it's these types of circuits that if you put inside the power modules, you can be promoting reliability. You can be doing two things simultaneously, shrinking and promoting the reliability of the electronics. So I thought I would mention some of these as sort of the DNA or the building blocks of things that I feel like I want you to take away from my talk, which is integration is a pathway toward greater reliability. So, what it comes down to is how do we assess this? And again, I've got a picture here of our Hall effect device that we've developed in gallium nitride, and we're putting that inside the module to monitor currents. But what are the things that we want to measure that would help be leading indicators of degradation? This helps us do the prognostics and diagnostics and apply things like machine learning algorithms to failures in the field. And as a result, we're able to be proactive on the maintenance and so forth, but with an informed method. And so, in fact, one project that we have done recently is putting sensors inside gas turbines. So you're putting these 400 degrees C, 500 degrees C electronics inside the blades of a gas turbine, and it's simply for operational maintenance. It's so that you can understand how things are starting to change and when it's time to schedule maintenance, and you don't have to do it on a predetermined schedule, because downtime for a gas turbine is just losing your chance to print money, because it's electricity being generated all the time. And so obviously the downtime is big. So these first three bullets here, the things to measure, the things to model, and the prognostics and diagnostics that matter for a given system are where there is a tremendous amount of work that's being done. But there's also some very clever work being done in fault-tolerant design. And this, again, is where we think integration. We may be adding some additional circuitry or components in order to be fault-tolerant. We certainly aren't doing this to sacrifice the reliability. And this is also where we get into hybrid types of systems. We may not be dealing with strictly wide bandgap systems in these cases. There could be a mix of material systems, silicon carbide, gallium nitride, whatever is the best for the solution as it relates to the fault tolerance we're looking at. And essentially, longer lifetime, or at least predictable lifetime. So in this particular graphic you see here is, well, efficiency may be one of our targets, but if reliability is also one of our first order targets, like in that module, and ultimately the applications it's going into, then we start to consider what is the right circuit to design and what are the things I need to design into the system and into the modules from the ground up. So I believe my last slide is one that kind of illustrates my point. This is a grid-connected device that goes from battery energy storage to a 13.8 kV connect medium voltage, and it has no transformer. So it's a multi-level converter. And in this multi-level converter, you see the classic several stages of cascaded H-bridge, okay? But in fact, we have developed this what we call XH bridge, which has a couple of extra switches and a capacitor here, and it allows us to introduce a degree of fault tolerance and a higher degree of reliability by simply replacing one of the cascaded H-bridge stages with this one. Because now if any of these cascaded H-bridges goes out, this topology boosts the possibility, offers the possibility of boosting the voltage by 2, and we can take a 7-level, what's normally a 7-level converter, lose an entire cascaded H-bridge level, and maintain a 7-level converter. And so in that regard, we actually are able to make that up and even promote greater levels of conversion, so and greater levels of efficiency. Yes, at the expense of a few additional switches, but what you see in the curve on the right is this proposed topology and its reliability prediction based on Markov modeling and predictive modeling. The conventional cascaded H-bridge itself, this is your lifetime, as compared to the proposed topology and a few key references which have also made some improvements. So people are looking at this, how we modify our circuits to be a bit more fault tolerant. And I will just conclude with this point right here. 2 key takeaways, maybe 3. Integration is certainly one, and that's down to sort of the technology or modular level. The modeling of the reliability so that we can do it as part of our multi-objective optimization work early on, so that we can take it as a first order impact and effect that we want to optimize to. And then 3rd, there's still room for a lot of creativity here. A lot of circuit design techniques that can help us promote better fault tolerant designs. And in certain mission critical or critical infrastructure type of applications, we definitely need that. So I'll stop there. Thank you.
All right, thank you, Professor Mantooth. It's a little unsettling to not be able to hear like clapping or anything like that. But we'll assume everybody's on board. I wanted to pass along sort of a question or two for you before we move along to Professor Jahns. You've mentioned, a variety of different things here that maybe we wouldn't hear in a typical power electronics talk, right? You're talking about cybersecurity, you talk about algorithms, you talk about heating and cooling, right? Thermal. So just for the, I assume there are a lot of students in the audience. How would you advise students going forward into the future, the next generation of power electronics engineers, regarding the clearly multidisciplinary aspect of making power conversion and power systems reliable and all the other things that they're supposed to be?
Very good question. Thank you. I used to tell students about 15 to 20 years ago that people who were in power electronics had an S on their chest because they had to be both hardware folks and software folks, because power electronics are embedded systems, right? We have digital control of everything. But in fact, now it's even more so. The advice I would give them is, you hear this phrase lifelong learning as it relates to us as we go through our careers. And I would just say, you need to really view power electronics as a journey, because it's an ever evolving field. And where we stand today, there are certain types of power electronics we design where they're very well understood. Silicon is king and it's the right solution and it's quite reliable and it's the way to go. And there's other more emerging areas perhaps where wide bandgap has a role to play. So you're having to learn a little bit more about a new widget to design with. Okay, that's good, that's exciting. And the controls are what are evolving so much. Now we've got thermal, we got reliability, all these other things that Alex asked in the question. And I think it comes down to this. No one's going to be an expert in all of these things, not one single individual, but you work with people who are great teams. So when I think about the projects that we do, they're mechanical engineers, electrical engineers, and computer scientists in some cases for this big data to help us understand how we might build a better system. And so you kind of take ideas from a lot of, and I think that's the thing for the students to take away is it's a team effort to do this sort of thing. Learn enough about it to be able to have an intelligent conversation, but don't necessarily be expected to know it all. Too much pressure.
That's a great answer. One more question for you. This is regarding, you know, higher temperature operation of modules. And the question is, you know, what happens if other components other than, say, the switching device are also limited by temperature? Do you see trends in the future for other components like capacitors or control ICs or anything like that to be able to also operate at those very high temperatures and take advantage of what silicon carbide, I think, is specifically what this questioner is asking about?
Very good question, and I have two answers to it. One is, of course, we need to pursue technologies that can operate at higher temperatures. Silicon on insulator, for example, recently saw some SOI work that's working quite good at 300C. Not that it couldn't before, but this was working long-term reliably at 300C. Then, of course, there's things like silicon carbide circuits, like I was mentioning. There's optical isolation that we've developed that is operating at elevated temperatures, and the sensing. So that's one axis, is getting all the parts that can operate at the elevated temperatures. Even if you're not going to operate them up in that regime all the time, making them that capable should improve their reliability under the normal circumstances at the 150 and 175 things that we try to keep things below now. And then the other point to be made there is clever arrangements and packaging architectures and thermal management that can be not the old sledgehammer, throw a big heat sink and a bunch of water at it to cool it off, but more clever advanced thermal management techniques that allow us to do controlled thermal. And so in this regard, we can have devices inside even our modules that can't take as much heat as the semiconductors, but we can also direct the heat away from those with proper layout techniques and also you know, even directional thermal management. So there's techniques to be addressed there. And again, this is a multidisciplinary problem there. So I think both play a role in the answer there.
Fabulous. Thank you very much. I think we'll conclude with Professor Mantooth for the moment and circle back at the end, which means that Professor Jahns is the next up on our list. I don't know how to change the thing. I think Mohammed's in charge of that.
Yes, it's Dr. Jahns. Yeah.
Yes.
Okay, I hope that this will come through shortly. So I'll put myself in presentation mode. Can you confirm that you can see it?
Can see it.
Okay, good. Let me try to get myself in presentation mode and see if I can get myself a little laser pointer here. Okay, I think I'm ready to go. First of all, I want to thank the organizers to give me a chance to make this presentation. It's great to have an opportunity to participate and learn a little bit more about this conference that I haven't had an opportunity to interact with until now. In the short time that I have with you, I thought that I'd pitch an area which probably in some ways is a poster child for issues of reliability, and that's aerospace. And I think this is a very timely period to have this conversation because, as some of you may be aware, there is a growing excitement about the possibility. At this stage, it's still in the early stage, but the possibility of electrified propulsion for aircraft. And fortunately, at University of Wisconsin, we have an opportunity to at least play a bit of a role in that, and it's been quite a learning and daunting exercise to recognize what we're up against. I'd like to share a little bit of those insights with you in this presentation. First of all, I thought I would, for those of you who haven't had a chance to visit us way up here in the North Country, give you a little bit of an idea of where we're at. I'm sitting right here, not here on campus, here, but not too far away from here, the center of our fair city of Madison, which is, as you can see by the domed building, is the capital of the state of Wisconsin. And we're blessed with a series of 5 lakes, and 2 of them form this isthmus that you see, and the university is on the foreground on the right. So I'd also bring the greetings of our group, Wisconsin Electric Machines and Power Electronics Consortium, WEMPEC. WEMPEC has been around for a long time. Actually, we're just, this is the year that we're celebrating our 40th anniversary. And to that point, the person you see in the very front row there next to me is none other than Professor Don Novotny, who is one of the 2 co-founders. The other co-founder, Tom Lippo, I'm afraid we lost just about a year ago. But Alan referred to the wonders of working with a great group and the importance, and I feel very fortunate to have just that in terms of the colleagues that I work with and many others in other departments that we have to draw on as well, and certainly our students, which is always a sort of great source of great inspiration and great new ideas as in any university environment. So this whole presentation I make could be talking about why electric propulsion and for aircraft and whatnot. I don't have that luxury. I really do want to focus the majority of my time on the issue of reliability. But nevertheless, for those of you who haven't really become aware of this, there is this growing excitement about the prospect of electrified propulsion for aircraft. It's part of a larger electrification. Really, it amounts to every mode of transportation, whether on the land, sea, or the air, are going through some stage of electrification, and is truly moving into the air as well. Some of the real driving reasons for this, I mean, why do it? It's not just for the sake of electrification by a long shot. In this case, it has actually a lot to do with greenhouse gas emission reduction. It turns out that as efficient as aircraft are as far as per passenger mile, turns out that release of any kind of greenhouse gas emissions at these kinds of altitudes, there's really an amplifier effect that goes along with that. And so anything that can be done to either reduce the fuel consumption by making the aircraft more efficient, or even more desirable, finding ways to move away from fossil fuels, those are all highly desirable. And together they provide a pretty potent drive for the and motivation for the initiatives that are underway focusing on this area. And really, in the long run, I think there's no doubt about it. It really does have a potential to revolutionize air travel. And certainly one of them that gets a lot out of the buzz is what you see in the upper right, the whole idea of urban air mobility, and each having our own little electrified drone to fly around and smile and as we fly over the crowded highways below us. So we'll see exactly how that comes along, but it's still exciting whether you're talking about commuter-sized aircraft all the way up to the wide-body aircraft at the other extreme. But let's talk about really what the challenge is when it comes to reliability. And really, when you look at it, it's really incredible how daunting it is. Let's first ask the question: what's expected these days in terms of reliability for a commercial aircraft? And really, the numbers that are sought after and achieved for in terms of failures per hour lead to mean times to failure that are on the order of 114,000 years. That's 10 to the minus 9th failures per year. And in order to accomplish that, typically what's demanded of the propulsion system is kind of like another order of magnitude reduction in the failure rate, where now you're actually across the threshold into over 1 million years in terms of mean time between failure. Right? I don't know about you, but every time that, at least in the past, when I would have an opportunity to get on the aircraft, I was very happy that so much energy and time was put into making these aircraft as reliable as they are. Okay, so if we're going to electrify these, where are we right now? If one looks at a motor or a motor drive that's used in state-of-the-art applications, where are we on this span? Well, it's not too pretty of a picture. Typically, it's generally considered that the most standard motor drives fall in the range of somewhere between 10 to the -5 and 10 to the -6. So if you turn that into mean time to failure, you're talking about somewhere between 11 and 100 years. And so, you know, for any of us working in the field, you know, these numbers are credible. In fact, 100 years would be pretty impressive for standard commercial drives. So when you look at it, you say, oh my gosh, look what we're up against. We need to get not just, you know, double or triple. We're talking about between 4 and 5 orders of magnitude improvement that we need in terms of reduction in failures per hour if we're going to expect to be able to compete with current technology. So this is just truly a daunting task, and it really is a challenge for this generation, and I'm sure those of you who are students for generations to come, to find ways to be able to address this. So, I mean, at first blush, you say, well, that looks hopeless. How would one even manage to imagine how you're going to get that kind of level of improvement? And there's no doubt about it. This is a challenge. And so it's a good question of, you know, how can such a huge reliability gap be closed? In order to do that, I'm going to spend a little bit of time talking about the wonders of concepts of, briefly, redundancy and repair, and then spend a bit of my time focusing more on the issue of motor drives and fault-tolerant motor drive design, and what the impact of that is on the machine, the power electronics, and this concept of integrated motor drives. And I'll close with a little bit of discussion of this project that I alluded to that we're involved in that's bringing us face to face with some of these issues. Let's deal with a very simple a case as you can get. Let's just choose a single motor drive, and there it could hardly be simpler. I mean, if a failure happens, most likely it brings the system to its knees in most cases, and we move, if we look at it from a Markov chain analysis, from a healthy state to a failed state. Now, I don't think you have to be a genius to say, well, you know, maybe what if we have a redundant system? Let's have 2 machines and a gearbox connecting them so they're driving off one shaft. Let's design it so that we only need one of these in order to be able to continue to operate. In other words, that's a remedial state. It's not a failed state. It's only when both of them fail that you would enter that failed state. And I'd like to introduce what turns out to be a really incredibly important part of this is the concept of repair, and I just circled that on the right there. That is, there's the opportunity, if you go into a remedial state, to have that recognized and to have that repaired, and depending on how quickly it can be repaired, often referred to as mean time to repair, that can be an incredibly potent handle on trying to increase the net reliability that has reduced the failure rate of this overall system. For even this kind of simple system, if you go through the analysis and use some typical numbers, as far as I mentioned, something on the order of 10 to the 5 mean time to failure in terms of 100,000 hours, that would be, you know, pretty good for you know, to be able to achieve something of that sort. And basically what one finds is that, I mean, what that means is that with no redundancy, you know, by the time you're getting out to, you know, 10 to 11 years, you know, you're getting pretty far down on this curve, meaning the more likelihood of a failure. Now, by just purely redundancy alone, it helps. I mean, it really almost doubles, in fact, the probability of healthy operation at the end of those years, which sounds about right if you have a redundant system. But this is with no repairs. What really gets exciting is when one recognizes that and finds that if one can introduce this serviceability and reduce the amount of time it takes before one institutes that repair, there's an opportunity, and just in the simple case of 2 motor drives coupled, of getting a boost of essentially an order of magnitude. And the shorter you can make that period before you perform that repair, the better it gets. So, I mean, this is just a clue of what needs to be done in order to take what otherwise are components that have finite lifetimes and find ways to turbocharge it, to find ways to increase it by not just 2 or 3, but by orders of magnitude. Fortunately, it turns out that when it comes to electrified aircraft propulsion, there's already trends in the direction of distributed propulsion architectures, and it's not being done necessarily specifically for redundancy. As you might imagine, this certainly lends itself to it, but there's concepts that I don't certainly have time to talk about it here, and I'm not the expert, but if I were, if we were talking about this from an aerodynamic standpoint, there's concepts of boundary layer ingestion that actually show that by distributing the propulsion along an airfoil and controlling the airflow over that airfoil, that there's ways that you can get a boost of between 10 and 20% in terms of the lift to drag ratio. And that's a big deal in something like this. But it turns out that these kinds of schemes, I mean, you don't have to be a genius to say, wow, if I've got this many machines, that looks like maybe this is the right way to go in terms of being able to achieve the kind of redundancy and repair capability that would move me in the direction at least of being able to meet the very demanding requirements for this kind of application field. I'll just have a very brief time. I just wanted to make the point that if you're going to deal with a redundant fault-tolerant system, you really can't afford to ignore any part of the system, and least of which is to ignore the motor itself. Fortunately, there are a variety of concepts that are out there. Some of these have been around for a number of time that involve concepts of modularity. That is, rather than having only a three-phase winding, designing the machine in a modular fashion so it could perhaps have multiple three-phase windings, as shown here in the upper left. There's other schemes that use, rather than exciting only one side of a three-set winding, excite both sides, so-called open winding. Or who says we need to be limited to three-phase? Is there anything wrong with going to 4 or 5 phases or even higher numbers? The answer is absolutely not. And so there are schemes, there's different machine types which have different characteristics, and there's a variety of different configurations. And so there is a rich opportunity, but also many challenges, because the goal here is to introduce this kind of modularity without introducing any performance penalties. The demands for power density are so intense for this kind of application that the thought of sacrificing power density for modularity is just a very, very painful choice to make, because it's not a matter of either or. We need both of them at the same time. As far as how one goes about doing it, there's a whole variety of ways. I mean, some of them are rather brute force of putting two machines having share the same shaft. There's schemes here that are, start to emphasize the concept of modularity, of having, in this case, 4 groups of three-phase windings that can each be excited with its own inverter. Or one could go a further step and actually isolate it down to the individual phase and excite each phase with an H-bridge in order to go another step up this ladder of fault tolerance. Now, which one is best? There is no one answer to that, but it's again, it's exciting to see that there are a variety of different options to pursue. Again, a topic that all I have a chance to do is just highlight at the very highest level that this also extends into the issue of the power electronics for the motor drives. There's been a variety of concepts, and this gets to the point that Alan made, is that sometimes by adding additional components, you're actually able to improve the overall reliability of the system because of the way that you introduce those extra components. And those are represented here, where you see extra phase legs added in and ways to be able to, on demand, bring in an extra phase to replace a phase that's failed. Again, very rich topic, and again, could easily spend a couple lectures on these kinds of topics and not exhaust it. Where it really gets interesting is we start to look at it as a system. And one of the concepts that I've been interested in for a long time is the concept of integrated motor drives. It is taking the power electronics, which as we know it now is located in a separate box, and use the fact that power electronics is an embedded technology, to take that literally and embed the technology, in this case, the power electronics, inside the machine. What you see on the right is one of our latest developments that's actually based on a current source inverter scheme rather than a voltage source. Now, one of the things I'll point out, why would one want to do this? Well, again, I don't think you have to be too much of a genius to imagine that if I can put these all in a single housing rather than having separate housings, that sounds like it might be a good idea in the name of high power density. You saw that several of the concepts that I showed you had multiple three-phase sets with a lot of different machine winding leads going into that machine. Well, each one of those is another lead that has to come out of the machine and get connected to the drive. One of the advantages of these integrated motor drive concepts is that all of those all of those leads are really almost invisible and almost zero, because essentially the power electronics is mounted immediately adjacent. So you don't pay the penalty of having all these extra cables interconnecting the drive box to the machine. I could go on, but I'll just point out that the flip side of this is that by doing this, you're putting this in harm's way in terms of thermally, EMI, vibration. So those are the challenges, very real ones, that go along with moving in this direction. But I'm convinced that in the long run, there's some major advantages that outweigh any of the challenges that we have to overcome. This is a concept that we have pursued. Again, I wish I had more time, but the idea of recognizing that, hey, anything that fails, whether if it's a controls, I mean, that's a potential single point failure. Is there a way that we can address that in the way that we design our modularity? This takes the granularity of the modularity down to the individual phase unit that you see here. It's kind of a building block that we would use to assemble a full inverter here. The idea is that this includes, of course, the machine winding and the iron tooth lamination, the power electronics to excite that phase, as well as the controller. So this makes up the total, with the idea that if one of these controllers fails, or anything fails associated with this, that the others still have all of their faculties with them and all of the power they need to essentially close ranks and be able to make up for that lost phase, and actually do it in a way that can actually eliminate the divot in the torque that otherwise would be present if you didn't make adjustments in the way you excited the phase. So again, exciting concept, and I wish I had more time to talk about it, but I think it at least points some of the directions of where some of this technology is going in the future. I want to point out, as I indicated, I would just a little bit about a project that have the privilege of working on together with colleagues at Ohio State University and University of Maryland, and actually North Carolina A&T as well. This is for a 1 megawatt machine. It's done under sponsorship of the NASA University Leadership Initiative. And this is a scheme where the goal is to design a 1 megawatt drive system in as small a size as we can. And that's not only the machine, but also the power electronics. And so we actually are taking an integrated motor drive concept and are using a modular approach in a way that allows us to break this drive up into parts. And in this case, we're actually exciting them in pairs, such that each of these is excited at only approximately 700 volts. And by connecting them up in series, it gives us the ability to operate this overall system at albeit low, a medium voltage level, even though the individual inverter only has to operate at a fraction of that voltage. And that turns out to be incredibly valuable for this class of application because of the challenges of partial discharge and the fact that electrical breakdown of air happens at the kind of altitudes where these aircraft fly at voltages about a fifth of what they would if we were doing this on land base. So there's a lot going on here and new challenges that have to be faced. And it's been a real challenge, but a real privilege to have an opportunity to look at opportunities to introduce this kind of technology. And this is what we're headed towards on the right here, a full integration of the power electronics and the machine all in one assembly. We even had an opportunity in an early phase of this at kind of a concept demonstration to actually find a demonstration. It happened unintentionally, but this is a case where we had 6 winding sets excited, broken up into 2 groups of 3, and once you know it, one of these, the breaker popped on it, and of course that means we lost excitation to half of the machine. And sure enough, just as we were expecting, the torque did drop. It's going to, but it dropped to 50%, and it did it after initial transient, but settled in very nicely at 50%. You might say, well, what do you pay for that? Well, one of the prices is that because of the unbalanced, the fact that we're exciting now one side of the machine, it is harder on the bearing. And so the issues of how you balance all of these design issues is clearly part of the challenge. There's no free lunch if one is going to tackle this kind of issue. So in conclusion, you know, right now, a lot of the focus that's going on right now in this whole area of development of electric propulsion is really focused on the power density. And I get it. I understand why that is as important as and exciting as that is. But the point is that really only gets us partway there. The issue is that the reliability has to get designed in right from the very beginning. It's not an add-on that you can add in at the end and expect to be able to get this, you know, this level of improvement that we need over conventional technology in order to be able to even be considered seriously for this kind of daunting aircraft application. Redundancy, I don't think there's any question that's going to be key. One thing that I didn't get a chance, but Alan referred to, is the idea of being able to recognize faults before they happen, that is incipient faults, and therefore trigger repairs before it even gets to the point that a module has failed. Those are the kinds of techniques we need to close this, this reliability gap. And there's just no two ways about it. It's a system issue. It's not just the power electronics. It's not just the motor. It's the controls. It's the power supply that's supplying the power to the motor. All of those have got to be part of the solution if we're going to be getting to where we need to go. So it's exciting. We're on the road, but boy, we have a long way to go. And for those of you out there who find this kind of concept interesting, there's a lot of exciting work that you can do, and plenty of years of effort that are going to take to accomplish it. So it's a pleasure to have this opportunity to give you this presentation, and I hope it's given you a few things to think about in just how daunting these challenges can be and what we're going to have to do in order to move in the right direction to solve them.
All right, thank you very much, Professor Jahns. We've had a couple of questions, and maybe I'll rope Mohammed in on this one as well. We've had a couple of questions just asking if slides, both from this set and the previous set, and I assume the next couple of sets as well, can possibly be made available after the conference to refer back to.
Can I comment on that? So if the panelists are confirm it, yeah, I can ask them for the slides and put it on the TPEC website.
That's probably the best way to handle it. So why don't we do it that way? So I'll certainly be happy to try to help out in that regard.
Sure, thank you.
Now, a couple of technical questions for you. You showed a graph earlier in the presentation that was showing the reliability of I assume it was sort of a jet engine system as opposed to a typical motor drive. And you showed there's, sort of 4, maybe 5 orders of magnitude difference between those two in terms of reliability. Where do typical motors fit in as opposed to the motor drives? Are they a much higher reliability than the drives, or do they both need substantial improvements?
You're touching on a sensitive point because I've been around for a few years, and the issue is, in general, the machines have and deserve, a deserved reputation of being more highly reliable than the power electronics. In fact, that is one of the major arguments today that I've run into for a long time when it comes to integrated motor drives is, why are you going to take such a high reliability machine and ruin it by embedding the power electronics in it that's going to fail long before the machine fails? Well, that, I have to say, is probably one of the biggest challenges that those of us in the power electronics profession need to address. I mean, things have gotten a lot better. I don't think there's any question that we're, order of magnitude or more better than where we were at the time when I first got into this field, but we still have a long road to go ahead of us. And I'm convinced that through concepts of using this kind of full court press on everything, starting from the component level all the way up to the system level. I mean, starting from the power semiconductor devices all the way through up to the issue of fault-tolerant motor drive configurations. That it's going to take all of those things. Machines do have their failure mechanisms. In fact, at high altitude, the issue of partial discharge and winding life is more of an issue than it is for comparable voltages at ground level. Issues of bearing life. I mean, it's not as if the machine is indestructible and doesn't have its own challenges, but I would dare say that the power electronics is still kind of the tall pole in the tent when it comes to overcoming this issue.
Great. And then one more question. This kind of comes back to the aircraft more so than the power electronics, but the question is, you mentioned that there's sort of a multiplier effect on greenhouse gas emissions when you do it at high altitude. So is there a notion to use perhaps, fossil fuel based propulsion to get off the ground, right, for lift, for takeoff and maybe for landing, but then electric for sustained flight? Is there sort of an intermediate path between a fully electric and a fully sort of fossil fuel based aircraft?
Excellent question, and I do want to encourage any of you who want to learn more about this, that there is a study that was done by the National Academy of Engineering a few years ago, and that publication is available for download, I think for free. It's only if you wanted a hard copy that you have to pay for it. And that one really spells out, and it's kind of interesting to watch the parallels of what's going on in the aerospace compared to what happened in land transportation, is that there's a lot of interest right now in hybrid configurations. That is, schemes that do not, excuse the pun, jettison all of the jet propulsion, but combine it in intelligent ways with electric propulsion, so that each can do what it does best. And the intuition of whoever posed the question is actually headed in a very appropriate direction, because it turns out that once you're off the ground and flying at high altitude, you need much less power to do that. And frankly, that's the point where you're at those at the layers of the atmosphere that become more highly sensitive to any emissions. So the idea of preferentially using the electric in that portion of flight in order to reduce the impact on the emissions is exactly one of the concepts that's being pursued. One of many, but one of them that is receiving serious attention as a way to be able to try to find ways to make the most of our imperfect technology that we have right now. And despite the the limited power density of batteries and other electric energy sources compared to jet fuel, are still coming up with aircraft like this one that still can deliver some really significant improvement in terms of net greenhouse gas emissions compared to conventional aircraft.
All right, great. I think in the interest of time, we will move on. There are a couple of questions left for you, Professor Jahns, in the question and answer. And so if you'd like to take the time to type answers to those in there, you'd certainly be welcome to do so. I think in the interest of time, we should move to Dr. Stork next. Are you ready to go, Dr. Stork?
Yeah, I'm ready. Mohammed, can you
Yes,
give me
actually,
I logged on also as a different user, and I could control it from there. Here you can see that, but I can't find a way to use sharing my screen. Okay.
Yes, do you want me to share it, or?
Well, it's the one I'm speaking to by the video. I cannot control, but I have another computer open here, so I'm logged on twice.
Okay, so then I can ask them to promote the other account to a panelist. I guess the other account's name is Hanson Stork, right?
Yeah.
So I think now the technician will do that.
Yeah, I think he just kicked.
Done.
So
I think he just kicked me out, actually.
No, I think you should be.
Should be up there. Well, it's something lost here now. So let's not bother. Why don't you
Sure,
move the
yeah.
slide,
I will
for
share
me.
this.
Hopefully I can sort of read on two screens at the same time. Thank you, first of all, for me as an industry sort of executive to participate in a highly technical set of discussions. There was a time when I did all this work myself, but it's been quite a while ago. And if you go to the next slide, I try to make a couple of points in, way too many slides that I have about specifically the reliability challenges with the wide bandgap devices. They are extremely popular right now as a field of renewed sort of ability to manage power at higher densities and with higher efficiency. But they are different materials than silicon, and there's a lot to be learned about them that sort of limit the expectations we can have on reliability. I'll talk about silicon carbide, and I'll talk about GaN, and then eventually talk a little bit about the packaging needs as well, because the semiconductors by itself is not enough. Next slide. So start off with silicon carbide. My sort of standing joke is that if you worked in any kind of alloying, that a few percent change of materials can make a drastic difference in the material properties. I personally had experience with silicon germanium, which is maybe 5 to 10% of germanium. Silicon carbide is 50% carbon and 50% silicon, right? It is a huge difference from silicon. Even though it sounds like silicon, it is far from that in many ways. Yes, we can produce substrates that we can cut into wafers, and we can handle them with the same machinery and similar processes with modified conditions. But one of the big challenges today is still a lot of substrate sort of defectivity. Good materials in this kind of world is 10 to the 4th sort of defects per square centimeter. That compares with probably sub 1 for a silicon device at not only 8 but say 12 inches. We do epitaxy typically for building devices that reduces the defects considerably, but it's still a challenge to kind of minimize that. Next step, next slide. And the first thing that happens, or maybe the other thing in every semiconductor reliability is the interface with dielectrics. Silicon oxide is rather blessed with having a near perfect sort of semiconductor insulator interface. That's in addition understood now for 5-6 decades with lots of study. And you see on the left sort of this band diagram how different the band gap picture looks from a silicon carbide point of view, which is 3 times the size of silicon and has different band alignment. So as seen in the middle, the tunneling effects are different. They need to be characterized or recharacterized. And then those are the intrinsic effects, but the extrinsic effects is the pure tail of the distribution, as you see on the right end, is still significant, and we need to figure out ways how to screen these devices out from the population. If you look at the next one, that sort of makes the point around, well, first of all, on the device operation side. Like in any semiconductor material, what happens at this interface, what happens right around the transition when the device turns on is rather critical. Mobility in silicon carbide is very subject to field conditions and intrinsically is not very high. So even though the material has its benefits of withstanding very large voltages before it breaks down, and so you can use very little amount of material to support high voltages, it does not have very great mobility. So the optimization on running the device for our on parameters or otherwise, need to be really fine-tuned right at the edge, I think, where lifetime and other fundamental reliability comes into play. Next slide. And then with that said, right, so you have a couple of fundamental criteria, have then the extrinsic things, which both are still significant. Our understanding is limited because the database is limited. certainly in comparison with silicon, it's infancy. And so we need to subject all these things to a variety of stresses to continue to learn and build up the expertise. And then we need to sort out sort of the early part of failure from the bathtub curve, if you wish, and remove by screening methods sort of the early part. This is possible to a degree. We're learning that we can reach the same kind of levels of silicon devices, but at the same time establishing that, for example, burn-in on wafer level can be a good substitute, an efficient substitute for burn-in at the package level, which is tremendously much more costly, cumbersome, time-consuming. Is still sort of in the development phases, and until we have that kind of clean criteria, we're going to have to deal with higher exposure to reliability or failure problems. Let's move on to the next one. There are features that are intrinsically better. This one talks about avalanche energy being much more easy to handle in silicon carbide. Therefore, kind of an overprotection that is typically needed for a silicon device. In fact, a silicon carbide diode can provide that function sort of in support of an IGBT. But if you just purely design with a silicon carbide FET, you need much less over voltage margin and can handle these things, especially with a little bit bigger die. Obviously, everyone wants a minimal die, but we have some cushion there in terms of absorbing the high energy that comes with avalanche breakdown. Next one. I think this is sort of the final picture here. Let me just double check. Two more things to mention. One here on short circuit robustness, and no matter what kind of applications, there are conditions where the device winds itself, at least in a transient period, on the short circuit. It needs to withstand that for a period of time, 1.5, 2, 3 microseconds. And silicon carbide is considerably more robust than the silicon, counterparts. So we're going through these characterizations, which tend to be very application specific. And so it's one thing to specify this for a device generically, but typically you need to identify also what the circuit conditions around that are. And then last but not least, in the following slide, a discussion about, or a setup described, next slide, around the DV/DT sort of speed. We as a company, and I imagine most other sort of power delivery, semiconductor delivery, do screen these devices for repetitive, stress conditions. 168 hours kind of minimal, 500, 1,000 and so forth are more typical. Cycling in temperature and in stress conditions. So we have these setups to do that. And all I wanted to just share you that for the silicon carbide world, these things are still actively being developed. And as we learn more about unique applications and their idiosyncrasies, the specifications may need to be sort of adjusted or at least better characterized. Let me jump on to GaN devices. And we skip the next slide. It was just a page on GaN. Now, the GaN is the other popular wide bandgap material, but a very different construct. As opposed to a vertical FET, MOSFET, or JFET for silicon carbide, the GaN devices are high electron mobility, heterojunction in a GaN AlGaAs layer that is built on top of a silicon substrate. Therefore, may be easier to use semiconductor equipment. It's already scaling up to 8 inches, for example. And it also has unique sort of device properties. There's no source drain junction, so it lacks things like avalanche and breakdown. But the HEMT structure intrinsically is very leak, is a very high gate leakage currents. You can also not extract the heat from the bulk substrate, but there's a lot of electrodes on the top to screen off voltages because the device is in principle in parallel planar. Now, we're looking at a number, variety of different ways to improve the ruggedness of these GaN devices. One is mentioned in the first talk about, integration. And this is one of the benefits of having a planar device. You can more easily integrate, other semiconductor structures with it, and that can help. The downside is you have to do it on a very expensive substrate. It's not like silicon where the devices are essentially for free. This is quite a bit more, costly. Of course, we can continue to improve on the process and substrate engineering, and then, we'll talk about assembly a little bit later. Next slide. One of the challenges around GaN is the differences in semiconductor sort of properties is noticeably different, even further sort of removed from silicon and silicon carbide. And so it's really important to understand the fundamental mechanisms and have agreement within the industry, across the industry, frankly, to adopt certain standards. The standards as been used and developed for silicon are, marginally useful, oftentimes overly conservative, and in other cases not conservative enough. And so there is this industry-wide, effort to bring these things together through IEEE as an example, and creating credible standards, as well as application notes for uses in equipment. Next slide. Just wanted to share this, that one of the challenges of any power device, but in particular in GaN, is sort of the safe operating area, because the device has some transient kind of phenomena. And so the way you operate the device has an impact on the performance characteristics of the device. And I'll talk about, I think, the specific one of RDS on in the next slide, which shows, no, the epi buffer was first. In part, I think this is contributed by epi buffer. I talked about GaN being epitaxially deposited on a silicon wafer. Because of the material constant being quite different, you have a buffer layer with different composition in between. Those layers tend to be full of traps, and in fact, they also trap a lot of the defectivity that doesn't rise to the surface, but therefore it also has electrical properties that need to be characterized. I got this material from one of my engineers, and it's actually surprising to see that some of the characterization here goes back to literature that goes all the way back to the 50s, when people studied similar phenomena sort of in silicon. And so it gives you an idea, by the way, that how early on, if you wish, sort of the learning of some of these mechanisms is in this field compared to where silicon has been. Clearly, we know that the base knowledge is much farther along, but there's still a rudimentary level of characterization necessary to get up to a same level of understanding as a silicon can have today. Next slide shows you the RDS on dynamics as a function of voltage. This is as I mentioned, intimately coupled to how you operate the device. It's a particular challenge during hard switching conditions. In fact, it doesn't really show up in soft switching configurations, but therefore, unfortunately, most of the benefits you can achieve from the speed of GaN, which is one of its key features, is in the hard switching applications. And so you have to solve that problem, or at least characterize, and so people can design with the problem in mind. And then last, I just wanted to show this cross-section simulation of heat distribution during switching, and how much is sort of happening at the surface of the GaN in this case, and how much actually it's equally visible here, but it's affected by the field plates design in sort of determining the static electric fields. And so the design can affect the statics of it, and then during the operation, you have to start modeling sort of the dynamics of the hot electrons in the channel to really predict, in a way, the degradation of the RDS(on). And it can be contained to smaller percentages, smaller and smaller percentages as time goes on, but sort of goes in tandem with understanding the material better, which was one of the early statements. Let me switch to the next one over and then go to packaging. It's kind of a transition slide here, but the packaging people, not unfairly, but they feel sort of, they are given these new materials and can only sort of subtract from all the potential if they are able to optimize the packages with those new conditions in mind. And so when you go to the next slide, it sort of summarizes many of the things they need to deal with. Things do switch faster, which means that parasitics at the package level become more significant. Things can operate at higher temperature, which means the package needs to support that, not only in the fabrication, but also during cycling and over its lifetime. This devices for the same amount of power can be smaller. Again, that has some dynamic properties, but also construction-wise, new challenges, etc. We'll talk a bit more about power density, in a minute. Next slide. One of the key things is you think about packaging, and that really stares hard at you, is sort of the mechanical aspect of it. So thermal-mechanical, in addition to the electrical, are sort of the threefold now packaging challenge with these wide bandgap, high power density kind of devices. One, on the top, you see a quick summary of how different silicon carbide is in modulus, in tensile strength, in hardness, and so forth than silicon. And those are the mechanical properties, but they matter. On a package level, they matter. Things break at corners. They always do, but they even more so do in silicon carbide. So we need different sort of ways to deal with the die size stresses during fabrication and during temp cycling. The next slide, you see some of the new sort of materials required to accommodate, the new power capability. Again, specific to silicon carbide, but you have a 3 times increase in potential heat concentration. The solder needs to be replaced by, silver sintering. The interface layers on substrates, need to move from aluminum oxide, silicon nitride. Heat sink attachments, need to be changing, and all of them allow a significant improvement, or maybe said in a more conservative way, otherwise prevent some of the advantages to be showing up at the package level or at the module level, as we will talk about in a minute. I'll skip over the next one, but I wanted to skip this one, and the next one go to the modules. As was illustrated before in one of the discussions, miniaturizing things is generally a good thing. We want to reduce the number of wire connections. We want to thin down the materials as much as possible. We want to eliminate any interface materials, fewer interfaces, more direct cooling, more efficient sort of transfer of heat, fewer parasitic inductances or capacitances. But you wind up with a device that is hard to see in real size, but it's maybe a couple inches on the side that can handle tens and sometimes hundreds of kilowatts, which is obviously just moving the problem to the outside world even further. So to wrap it up in a brief way, next slide. These wide bandgap materials are tremendous potential in terms of their electronic properties. They come with new features in terms of mechanical properties, thermal properties, as well as electrical characterization that finds itself still quite a bit of early on in the learning curve. And last time I checked, getting through that learning curve takes data, and the data comes from applications. And so we have no choice really but going through this early phase of getting more proliferated use of these devices, and there's a tremendous demand for them, so that's sort of accelerating that. But then beyond that, it needs a very broad sort of interaction, with the user, the application level, with the manufacturing piece, really very cross-functional to get these products out there at a total integrated level that is, as good as the material itself can support. So that's sort of my quick pitch on the wide bandgap devices.
All right, that's great. Thanks, Dr. Stork. I do want to pass along one question to you, and then I think we'll have to move on for time. You mentioned something interesting, and I was thinking about this myself as you started your presentation, that 70 years ago when we were working with silicon very initially, we as a society had to go through a lot of sort of push-ups to understand silicon and bring it up to a level of reliability that was sort of acceptable. And it seems like we're sort of repeating that process and going through some push-ups again with GaN and silicon carbide. So the reliability challenges that we do see right now with those going away eventually and sort of matured the technology, do you see the ultimate reliability of GaN and silicon carbide surpassing silicon or being about the same?
On silicon carbide, it would be a bit more optimistic, because fundamentally you use, the bulk material, you purify it a little bit through epitaxy, but you're working with one sort of material set. I think fundamentally with a GaN on silicon substrate, you have two very different material systems that I think are a little bit more challenging to bring to the same level of purity, as in the other case. They, whether they can really catch up, not in the next few years, as our understanding, and I would say it's a little bit of a vicious cycle here. I think as the applications can benefit from the devices, then more volume will quickly, materialize, and so the learning curve will steepen and we get close enough. Because it is in the end, a function of investment, right, to solve all these problems. And I don't think we're ever going to be close to that level of silicon. But then again, do we need to be exactly at that level? No, we're still building just discrete devices, so the criteria are also a bit removed from, compared to say, billion unit sort of silicon integration. So optimistic, but still a number of years indeed to go through.
All right, fantastic. I think we'll leave it off at that point. If there are more questions, they can certainly be still placed in the question and answer section. Let's, in the interest of time, since I think we're trying to finish up around 10 or 15 after 5, let's move on to Dr. Narumanchi and proceed with that presentation.
Yes, thank you, Alex. And I'll share my screen here. Quick confirmation, are you seeing the slides?
Yes, we can see it and we can hear you.
Okay, thank you. So yeah, good afternoon, everyone.
We are seeing your sort of presenter view, if you will. If that's what you want to show, that's fine.
Sure. Sure. Is this better?
Better now.
Okay. So yes, good afternoon, everyone. Yes, thank you for, thanks to Alex, Mohammed, and the conference sponsors, organizers for inviting me. This is my first time attending this conference, so happy to be here. Again, thanks to Dr. Mantooth, Jahns, and Stork for their presentations and overviews as well. I'm the group manager for the Power Electronics Electric Machines Group. This is within the Center for Integrated Mobility Sciences at NREL, National Renewable Energy Lab. I'm listing my group members here, about 12, maybe 14 staff overall, focused on thermal fluids, thermomechanical reliability aspects for both power electronics and electric machines. A lot of our work has focused on electric drive vehicle applications, but more recently going into other renewable energy and energy efficiency applications as well. So today I'll focus on the reliability aspects, and there certainly will be a thermomechanical thrust in what I present here. And I'll focus a little bit more on our group's work in this area. But yeah, reliability aspects for power dense electric drive power electronics. Talking more about power electronics here, but that's more a reflection of what we ourselves have done more of. But certainly, as Dr. Tom Jahns and other colleagues have pointed out, the electric motor machine aspects are very important as well. So it's useful to look at the pathway for electric drive vehicle electrification, though I think prior colleagues have pointed out the trend towards higher power density. But I'm showing here, this is the Chevy Bolt going to this, the main point is increased power density, more compact footprints. And I'm taking this from the Electrical and Electronics Technical Team roadmap. This is a roadmap that guides the activities of the Vehicle Technologies Office under Department of Energy. But similar thought process, I think, apply to numerous other programs or even thought processes from our industry colleagues. So increased power density, reduced cost. These are some numbers that are listed here. And then the important topic of reliability and lifetime. So 150,000 miles for light duty on-road electric drive vehicles, going up to 300,000 miles. And then for medium and heavy duty vehicle applications, going up to even 500,000 or even beyond. So certainly, and then the key is to do all this together. Again, another point I think Professor Tom Jahns brought up. So we want to keep the power density increase and the reliability improvements going together in parallel. This graph, it's my attempt at capturing the state of art and how it compares to some of these targets that have been established. A few commercial baselines listed here: electric drive system power density and inverter power density on the x-axis. There's the total drive, the total electric drive power density. So commercial baselines, and I've just positioned the targets here, just giving a sense of where things are headed. So certainly the big one is, you can see the increasing trend of increasing power density. So then on the power electronics side, so yeah, the point has been made, we want to reduce the footprint. Showing, this is just maybe a representation, a schematic representation. So there's an inverter photograph taken from our lab, commercially available inverter. So planar construction will help. That's at least one pathway. But the point is the 8 to 10 factor of 8 to 10 reduction in the volume size. Again, the key phrase, multi-physics integration challenge. That's what we are faced with. And certainly the various, our reliability will be a very important aspect here. Just maybe to elaborate on that, we have larger temperature gradients within the system, just because everything is going to be packed closer together, and come with those large temperature gradients comes all the thermomechanical stresses and the failure modes and mechanisms associated with that. So just in terms of what I'll talk about here, is various constituents of the inverter which have been described, but maybe I'll focus more on the package and power module. And Dr. Hans Stork presented some very interesting information about the devices and device packaging. Maybe I'll build on the device packaging or power module aspects from a reliability perspective. This one, I think I've introduced the 3 key focus areas for our group, maybe focus more on the advanced packaging designs and reliability. But we do have significant efforts on thermal management aspects, both within power electronics as well as the electric motor. So here I'm showing a cross section of a package or power module. I'll be using this graph fairly frequently. This shows the device. I think for all of our research programs now, or even development within industry, the thrust is on silicon carbide and gallium nitride device-based package, module, component design, development, and evaluation. So certainly these can go up to, the device itself can go up to 200 C, maybe even beyond. The point has been made. All the other layers need to support that operation, whether it's the electrical interconnects, the various attached layers, the electrical insulating substrate, the encapsulants. So we've been working along with the collaborators on improving the reliability of each of these technologies, developing predictive and remaining lifetime models. And that's specific to a failure mode. So I'm showing a bonded interface here, and this is a cohesive fracture that is happening. And that's what can happen under some of the thermal cycling and the stresses that can result in this. But the lifetime models, predictive models, are specific to the failure mode. And also we want to identify processes which help improve the lifetime of these components or subcomponents. The package parametric modeling, we work with numerous industry and research colleagues, helping guide the design and development of advanced module, package, inverter, converter configurations. And maybe that's one example I'll give, again, taking this cross-section as an example here. So we compute strain energy density within this substrate attached layer, and focusing on this graph here, strain energy density for different base plate materials, copper, aluminum, silicon carbide, and aluminum. And then we have, of course, the 3 different ceramic materials. So low strain energy density per cycle means, or it's an indicator of better reliability. We have seen that experimentally. So that's how this is helping guide design. This is showing the benefits of the aluminum silicon carbide base plate. It's showing how these different ceramic substrates stack up against each other in terms of performance. Also, the base plate thickness, increasing base plate thickness, that can increase the stiffness, and hence we are seeing higher strain energy density per cycle, and hence that may result in lower reliability. Same with the ceramic thickness as well. Increasing thickness means increasing strain energy density, potentially lower reliability. So again, I'm just, this is just as an example, the kind of thermomechanical modeling efforts we have performed and are performing to help guide our module, package, inverter, converter development. We are looking at various substrate attached materials, sintered silver along with industry collaborators, with Virginia Tech, with Georgia Tech on copper, aluminum, transient liquid phase, bonded interface materials. Some scanning electron microscope images are shown here. The way we do it is between copper and Invar, we have the bonded material. There's a significant coefficient of thermal expansion mismatch. And then they're subjected to thermal cycling going up to 200 degrees C, again, with a view to the higher temperature power electronics. Again, the temperature, and I'm not sure if I mentioned it, but worth mentioning again, it's an important knob to increasing the power density of the components, and hence the interest in higher temperature, at least for mobility applications. So these are the coupons on a hot plate, some of the cycling happening. We observe the interfaces under acoustic microscopy. Maybe some key conclusions here are, we do feel that the area of high temperature, 200 degrees C, power electronics, the large area attachments, there's certainly a continuing need for improving the reliability. So we do see some concerns when it comes to large area attachments. The reliability definitely could be improved. So that may be one overarching conclusion here from everything we have seen over the past few years, and even based on our own work. But it's certainly a very much a fertile topic for continuing investigation. We've been looking at substrate attach alternatives. So the direct bond copper substrate, active metal bonding, these are prevailing commercial baselines, but we have been collaborating with DuPont on organic direct bond copper substrates where a polyimide dielectric is bonded with a metal, and there's no limitations on metal material or metallization. The reason for doing it is very much from a reliability perspective, especially for higher temperature power electronics packaging. We've been looking at different configurations as shown here, at least as a starting point in terms of concepts, and we have performed thermal modeling to quantify the performance of these packages incorporating this Temprion material. I think thermally we can pull it off, if I put it that way. That's kind of the main message maybe I'm wanting to convey here. On the thermomechanical reliability aspects, the strain energy density per cycle as a function of top metallization thickness. This top metallization thickness, it's important to increase just from a thermal perspective. It is beneficial, but what happens to the thermomechanical behavior and reliability? So fairly flat line here, so not much of implications from a reliability perspective is what the key point here is. We have performed experimental accelerated testing and thermal shock, thermal aging, power cycling. This is all within our setups here at NREL. So maybe some of the key conclusions are these are withstanding fairly high number of shock cycles, 5,000 shock cycles, 1,900 aging hours, thermal aging hours, and 2,200 power cyclings. No degradation in electrical or thermal performance. So it's looking promising is maybe what the key conclusion here is based on all these experimental evaluations as well. We are looking at alternative electrical interconnects. This is in collaboration with Indiana IC and Oak Ridge National Lab. So as the current density, power density is increased, devices, packages, modules are reducing in size. So from wire bonds, we are wanting to go to alternative interconnects. So this is showing this quilt interconnects, as we call it. Mostly this is led by Indiana IC. And what we have done is we have looked at this kind of a package. So two chips quilted together on top of this DuPont organic direct bond copper substrate. We have subjected it to experimental reliability evaluations, sinusoidal vibration, mechanical shock, thermal cycling, following all the standards that are listed here. And we have performed electrical resistance measurements after the cycling. So sinusoidal vibration looks like it's looking fairly flat line here, but mechanical shock and thermal cycling can be fairly stringent, and based on resistance measurements of 1 ohm and higher, it's a definition of a failure threshold. Certainly the reliability could be improved. This shows the quilt interconnects, but also the attachment of the devices themselves, the solder or the bonded interface attached. That also, I think, is delaminating. There's a little bit of a confounding effect as can often happen, and that's where some kind of a torsion effect going on here. But overall, working with collaborators on trying to improve these packaging configurations. So future package designs, this is my last slide here. Certainly a lot of efforts over the past decade on double-sided implementations. So this is the Delphi Viper package, a lot of the Toyota implementations. We observe the polymeric materials greases are there in a lot of these commercial implementations. So looking forward, maybe some of these configurations shown here certainly get the grease out of there if possible, and then employing some of these polyimide substrates in either a double-sided or a stacked die configuration. Looking forward to working on some of these collaborators going forward. I think that was it. Yeah, I just want to acknowledge a lot of the work under various DOE offices and a significant number of industry, research, university partners and collaborators, and very much looking forward to collaborations, continuing collaborations or new collaborations with those of you in the audience. Thank you.
All right, that's really, really good. I did want to pass along one question to you, Dr. Narumanchi, and it sort of relates to a question that was asked earlier of Professor Mantooth. It seems like you're deeply embedded in a very much a multi-physics, multidisciplinary kind of world. So it's kind of a similar question. How do you navigate that, and what kind of expertise are you looking for in your team, and how do you get people interested in those areas? We've heard a lot about electrical aspects, and I think you've talked a lot about thermal and mechanical aspects. How do you get someone interested in sort of thermal reliability of, of materials and things?
Yeah, no, Alex, definitely multidisciplinary. So we work a lot with collaborators. Again, Professor Tom Jahns, Alan Mantooth, we have had interactions, collaborations. But yeah, it's all about, I think the point has been made, very much agree that the team for any given project, if I may put it that way, has to be an interdisciplinary team, and it usually is, addressing all the major physics that are involved in this. Yeah, I think multiphysics co-design is the way to go, and increasingly that's what we are seeing happen.
All right, I think there are more questions than we could possibly answer, but I want to sort of raise a flag for Mohammed here. I think we're at, roughly speaking, at time. So Mohammed, how would you like us to proceed?
If you don't mind, yeah, I think we can stay for Q&A and some concluding remarks. I mean, if you are on board.
It's fine with me.
Yes,
well, I think one of the funnest things that we can do in a panel situation like this is, I think all of the speakers bring an enormous amount of expertise and have sort of politely listened to their colleagues, but and allow the rest of us to ask questions and interrogate them. But I like to give an opportunity for the panelists to sort of ask some questions of each other. I think that's an interesting opportunity here as well. So let me just open that up for a little bit and see if you guys can interact a little bit.
I have this one question in a very general way around hybrid systems. Hybrid is always first proposed as the best of both things. But there's a flip side, there is also the worst of both, right? For example, in a car I'm more familiar with, but I imagine similar in a plane, you have more weight on all the machinery than in one alone. And weight matters a great deal when you want to put it up in the air. So is it really true that these hybrid configurations are long-term sort of a win-win proposition, or it's just really case by case? It's more of a philosophical debate, I think.
I'll try to answer that. I think that, I think that what has happened in land vehicles is actually instructive of what is likely to happen over the long haul with aircraft propulsion. I mean, what we've seen is that, hybrids really played an instrumental role in kicking off the transition to electrics, but it is a hybrid, and as you say, it in some ways it can bring the best and the worst. But looking back from now, I mean, it was a transition phase. It represented the state of the art of where batteries were at that time. Batteries have come incredibly far in terms of the needs of electric vehicles, and as a result, hybrids, although have not disappeared, they no longer at the center of the stage. And I look at it as reflecting the fact that they do represent kind of a transitional phase. And I think looking at the long haul, the same will likely be true for aerospace. It is true that you have to work hard for aircraft systems. From my observation, I'm not the expert, but I have had the privilege of kind of watching over the shoulders of some colleagues at Georgia Tech who have worked on the issue, and they have to work hard to come up with schemes that simultaneously meet strict criteria as far as weight, but still provide overall system benefits in terms of reduced greenhouse gas emissions and efficiency of the system. And I think it has helped to highlight for me, what those challenges are. I guess it's convinced me that it's not impossible, that in fact there are ways that you can demonstrate net advantages with hybrid systems, but it also highlights exactly the the issues that you describe, that you sense intuitively, that that you are going to have to work hard in order to overcome the disadvantages that go along with having duplicate, not duplicate, but you're going to have to be very smart in how you combine those components in order to come up with a net win at the end of it.
Thank you. Appreciate that.
Yeah, maybe just to add to Professor Tom Jahns here, yeah, certainly hybrid systems seems like they would be the good starting point. Again, the aviation example has come up, and also Dr. Stork, maybe I'll mention here, and I know Professor Jahns is involved as well, the ARPA Ascent program on hybrid electric aviation. So that's kind of represents a concrete effort, at least in terms of electrification of aviation, and the focus, I think, as a starting point is on hybrid systems.
There's no doubt about it that for aircraft propulsion, I mean, we're in terms of my profession, I'm focused on the machine and the drive. But when it comes to the long haul, as far as what is really going to make or break that, it's really what I just mentioned along with the land vehicles. It's tell me how power dense you can make the batteries, the energy storage. It's just hard to match what Mother Nature has given us in terms of the energy density of a gallon of jet fuel compared to what you can do with batteries. Now, we've come a long way, so am I prepared to say that we'll never get there? I don't, I doubt that I'll live long enough to be able to witness the answer, but I guess I'd like to be an optimist, given the business I'm in of being an optimist with regard to technology trends. So I'd like to believe that we will find a way. It may not be what we're thinking of right now, but I suspect that, and I hope that new solutions will come along that will pave the way for land, sea, and air transportation. They'll all benefit greatly, and particularly aircraft when it comes to the desperate need for that kind of super high energy density in order to talk about flying from from New York to Europe and back again, on batteries. I mean, we kind of laugh to imagine that now, but who knows? Things that a lot of people have laughed at in the days ahead. Turn back and say, "Wow, wasn't that funny that we didn't have the vision to imagine that things could go through those sorts of improvements." So we'll just have to wait and see what happens. But that really is a critical need. I guess one question that I'd like to ask with regard to materials and packaging. I mean, as my now late colleague Bob Lorenz used to say very often, is that packaging is just such a bad name for what goes into and all of the incredible multidisciplinary technology that goes into placing semiconductors into packages. I mean, as he would say, when somebody says I'm an engineer working on packaging, you kind of think, well, you work for FedEx, or what exactly do you do? But in fact, I mean, I've developed in my own career, even though I'm not an expert in an incredible appreciation and respect for the multidisciplinary nature of that work and its importance. I mean, you can have the most fabulously reliable chip in the world, and it ain't worth nothing if you put it in a package that doesn't have the characteristics that can take advantage of that reliability. And the same goes with high temperature. I mean, you can have your 600 degree silicon carbide chip, but show me the package that you're going to put it in that's that's going to match that. I mean, that's every bit as big of a challenge, and arguably in some senses at least matches. I won't say higher, but certainly is right up there, and ultimately has to be resolved. So I'm curious in terms of thoughts of other panelists and perhaps you, Dr. Stork and Sreekant, when it comes to materials advances, with all the advances in nanomaterials and all the fabulous opportunities, what do you foresee in terms of the long-term opportunities to even do such simple things as match the temperature expansion coefficient of some of the other components? I mean, if you could solve that would, I mean, that's not a new idea, I realize, but the problem is that we don't have the combination of characteristics that we need right now. But even if we could do that, that would be a huge step in terms of solving what amounts to so many of the sources of failures, which is fatigue at the intersection where two materials with different expansion coefficients meet and ultimately fail over X number of cycles, and that's just the way nature works.
If I may start, there's a couple of different thoughts. One, when I first got sort of connected with the power industry, the material science people draw my attention to silver nanoparticles. And, for years that was like, when is this actually going to happen?
Right.
and it's happening now, right? So specifically, there's a progress in the formulation, I think, of how you build the substrate material, how you deploy it, and the benefits that you get in terms of a more robust sort of connection. There are progress, in fine tuning, I would say, in dual bonded copper substrates. The insulator being both a very good thermal conductor and at the same time a very good electrical insulator. It seems like contradictory requirements, right? And yet, as people have gotten more progress on dealing with the interfaces and even the individual material choices, progress being made there. So it's definitely a part of the field, I think, to explore types of alloys, minimal sort of compositional changes to just optimize sort of the capability a bit better, and oftentimes significantly. Completely new materials. Copper is sort of standing out as sort of the best sort of conductor, with manageable properties out there. So I don't see much of a change there. We've replaced gold, wherever we could, pretty much because of reduction of cost.
Yeah.
So I don't know what the generic, response is, but there is a key element of material science in this world as well. And it is quite intriguing to see that it needs to meet both electrical and sort of mechanical and thermal sort of properties. Maybe not semiconductor electrical, but still, an electrical, sort of domain. And you come back to the cross-disciplinary aspect of that field. And if anyone is interested, I would highly encourage it, because it is, because of that, so interesting, with so many new innovations coming along all the time. So.
Yeah, certainly, Dr. Stork and Professor Jahns. Yeah, certainly as a community working hard. I think when it comes to temperatures, looks like we still may not be past the 200, 250 C junction temperature capable package. I think 200, 250 itself seems like a fairly stringent challenge. Yeah. So, but trying hard collectively, I think all the attached layers, the electrical insulating material, as Dr. Stork pointed out, which is still good from a thermal perspective and a reliability perspective, maybe encapsulants. So again, the copper-based systems that Dr. Stork spoke about, copper aluminum-based systems, it still seems from a cost perspective, that's where we are in terms of even these attached layers, or maybe on the electrical insulating materials, polyamides or other class of materials. That's where the focus is, keeping various constraints in mind. So, but it does seem like the temperature challenge is very stringent. We haven't gone past even 200, 250 yet.
Yeah. You made me think of one other aspect, sort of evolution in the packaging field, and it's a little bit on a tangent here, but we talk a lot about heterogeneous integration these days, and it's really the desire to closely package, devices with different substrate processes together. So maybe combining, silicon carbide and a silicon and a GaN, and or a highly digital component with an analog or a power component. The challenge I foresee on that is something along the line of the hybrid model, right? So, okay, now, yes, you can put your power device or an analog device and a digital device, but for which do you optimize it? Right? Can you optimize it for both in terms of performance, cost, form factor, all of these various aspects. It'll be another creative puzzle, I think, on finding. In some applications, we'll run with it. In some others, I think we'll go the old way and keep separate.
Thank you, both of you.
It's multi-physics co-optimization.
Yeah.
Maybe I can ask just one last question to wrap us up here. I think on our panel collectively here has an enormous amount of learning and wisdom across a great deal of areas. I also think as experts, still in our heart of hearts, we have things that we're really excited about and just get us, just sort of get us up in the morning. So I'm curious if you could each just spend 15 seconds, 20 seconds and just share with us what you're most excited about right now. What sort of is just really makes you enthusiastic. What technology or circuit or material, or what's the cool thing that you're either working on or that you've seen people working on, that just makes you feel like you're back in grad school again.
Alan, you want to start off?
Sure. I think in some ways I talked about it today, and that's the systems engineering aspects of what it takes to build next generation power electronics. And as for myself in specific, in my 5 seconds remaining, I would say that we're focusing a lot on the silicon carbide integration at the lower voltage levels so that we can have a more uniform material system overall. So we're putting a big effort into that, and maybe even have our own silicon carbide fab. So we'll be developing technologies that we think can roll out from there. So.
Well, I think my answer is along the same lines. I'm really excited just overall about the future impact of wide bandgap devices. I mean, they are making it possible to talk seriously about, seriously shrinking the size of the power electronics, having it operate at high temperatures. I really think I'm excited about being able to contribute to achieving the objective of having power electronics as a truly embedded technology, that is, regardless of whether we're embedding it into a light fixture or into a motor or into solar panel or whatever, but to be able to embed it there and get to the point where we don't even have to worry about coolants. It can take the heat, it can take the cold, it can operate in that environment and just be part of the system. I think that we still have a long ways to get there, but I mean, I think with the advent of the new wideband gap, it's opening up new opportunities, which certainly keeps me excited and wanting to come into the lab. I only wish I could these days, but nevertheless, still excited at the vision of the opportunities for advances in those areas.
I had my choice. I'd come in and work on these battery power converters. I think the prospect of the electrical vehicle is just beginning. There's so much more optimization possible and being thought of, more integration with the transmission, the axles of the device, of the car, etc. I think that progression is finally sort of breaking through in broad use, and I think it's very exciting to see that growing rapidly, and hopefully it really be a good thing for mankind in the end.
Yeah, so from my side, the power dense, reliable, low cost systems that we have been discussing, power electronics, electric motor, electric drive, seems like a lot of opportunities for innovation on thermal fluids, thermomechanical aspects. So yeah, excited about our group doing our bit, contributing towards the overall goal. So.
I think it's an incredibly exciting time in power electronics. I mean, I was excited about when I first got into it, and I feel as excited now in terms of the new technologies we have available and the new opportunities and the demand for it. It was suggested in terms of desperate need for ways to clean up and our environment and find ways to address the societal challenges. I think it's a great time for young people to get into the field.
All right, thanks very much. The thing I liked the most about that, I don't know if you guys noticed, but as each of you shared your thoughts at the end there, you each had a great big smile on your face. So I just think that's indicative of the state of where we are. And I just love to see that kind of enthusiasm. With that, I think we're pretty much concluded. I'll pass it back to Mohammed.
Sure. Thank you. Thank you all for joining this this session. We learned a lot from you. I appreciate it. Thank you.
Thank you.
Right.
Thank you.
Thank
Thanks,
you all.
everybody.
My pleasure.
Bye.
Bye-bye.
Take care.